Welcome to Unit 3, Session 1, Anthracene and Phenanthrene. So, under Unit 3, we'll be looking at tricyclic aromatic carbocycles, and we'll be looking at basically the two common ones, which are anthracene and phenanthrene. So, at the end of the session, you should be able to give IUPAC names for structures of substituted anthracene and phenanthrene. You should be able to draw resonance structures for both anthracene and phenanthrene. You should be able to compare the aromatic stability between anthracene and phenanthrene, and then also state the sources of both anthracene and phenanthrene. So on the sources, both naphthalene and phenanthrene are normally obtained from the fractional distillation of quota. And anthracene, for example, for instance, its oil fraction is cooled and pressed to obtain the solid crystals out from the liquid. So basically, after getting the solid crystals, it is purified through sublimation. Now on phenanthrene, when the crude is obtained, it contains both the phenanthrene and carbazole. And carbazole is completely different from phenanthrene. However, the solid is powdered and washed with naphthalene solvent, which dissolves the phenanthrene, and the remaining solid is washed with pyridine, which dissolves the carbazole. Since we are more interested in our phenanthrene, we use dissolution process that is able to dissolve only our compound of interest, which is the phenanthrene, leaving the solid carbazole to dissolve in pyridine. Okay, so next is to look at the structure and nomenclature of anthracene and phenanthrene. Now, these two compounds are obtained from naphthalene. When a third benzene ring is fused to naphthalene, you can either have anthracene being produced or phenanthrene being produced. So, anthracene has all the three benzene rings in the straight form, whilst in phenanthrene we have the benzene rings in a form of a curvy or U shape. Now, both anthracene and phenanthrene have similar structures. Yes, just as I said, with the same chemical formula, C14H10. However, they have different thermodynamic stabilities, and that is what we'll be looking at in the next slide. Okay, so to look at the thermodynamic stabilities of anthracene and phenanthrene, between anthracene and phenanthrene, we'll quickly look at the substituted anthracene and phenanthrene derivatives and their nomenclature. So this first structure is known as 1,2-dimethyl anthracene. This is also an anthracene derivative known as 9,10-dibromo anthracene. Then you can look at some phenanthrene derivatives as well. I think we've already looked at the numbering, so numbering shouldn't be the problem. So we have 4,10-dimethyl phenanthrene. We also have 9-chloro-10-nitrophenanthrene. So please take note how to apply the nomenclature in how to apply the numbering in the nomenclature of anthracene and phenanthrene derivatives. Okay, so now to look at the thermodynamic stability of anthracene and phenanthrene, we use the resonance structures. Now, if you look at anthracene, for instance, anthracene has 4 resonance structures with a resonance energy of 84 kilocal per mole. However, phenanthrene has 5 resonance structures with an resonance energy of 92 kilocal per mole. So, just as we talked about naphthalene in the previous slides, now the number of resonance structures is related to the stability. So, the more resonance structures a compound has, the more stable it is. Okay, yeah, so molecules with more resonance structures are said to be more stable, right? And if you take anthracene, for instance, out of the 4 resonance structures, only 2 contain fully aromatic stabilized benzene rings. This is one, based on the Fries rule. This is one of them. This is another one. So this resonance structure has 2 complete aromatic rings, and this as well. This has 1 complete aromatic ring, another complete aromatic ring. So please take note, just 2 out of the 4 resonance structures have fully aromatic stabilized benzene rings in anthracene. Now, if we come back and look at phenanthrene, now phenanthrene has 5 resonance structures, and out of the 5 resonance structures, 2 are stabilized through the complete aromatic stabilization of benzene rings. So if you look at this particular structure, it has two aromatic benzene rings. One, two. This one has one and two. So this has two benzene rings, which are complete, fully complete benzene rings. And look at the third resonance structure. Now this resonance structure has three complete benzene rings, right? So this number of complete benzene rings present in phenanthrene makes phenanthrene more stable than anthracene. So please take note. The number of resonance structures is related to stability. The more resonance structures that are formed, the more stable the compound is. And then, of course, if there are more resonance structures with full benzene rings, they kind of make the resonance structure more stable than those with less full benzene rings.